Select the best set of reagents to accomplish the following transformation. So we want to look at this and decide what has changed in this molecule. So we always want to see, have we changed the functional group and have we changed the number of carbon atoms? And the answer to both of those questions in this case is yes. So we can see that clearly that we have a benzene ring at each structure, and that does not appear to be changing. What appears to be changing is what's attached to the benzene ring. So we are starting with an alkyne, specifically a terminal alkyne. So that is an alkyne that is at the end of a carbon chain. And we're ending up with an alkane that's attached to that benzene ring. And we should count the carbons to see how this carbon chain has changed in terms of the number of carbons. So we have initially attached to the benzene ring 2 carbon atoms. And I could number the ring if I wanted to. I can see very clearly that those 6 carbons are the same, so I'm going to focus on the rest of the molecule that seems to be changing. So we have 2 carbon atoms to start with, and it appears that we now have a chain of 4 carbon atoms. So we know at this point one reaction that will allow us to build a carbon chain. As we progress throughout the course, we're going to come across a few other reactions that will allow us to also do something similar to build carbon-carbon bonds. But for now, the only thing that we know is that we can take a terminal alkyne and convert it into a nucleophile and have it react with an alkyl halide. So that's what we're going to do for this reaction. So if we want to deprotonate a terminal alkyne, we need first a really strong base. So it needs to be a base that is strong enough to remove the hydrogen of a terminal alkyne. So the base that we typically use for this is NH2 with a negative charge. So this is the conjugate base of ammonia. And so this is a strong enough base to remove a terminal alkyne hydrogen. So this is the first thing that we want to do, is to remove that hydrogen. And so what that does is that puts a negative charge on a carbon atom. And so that negatively charged carbon atom is a really powerful nucleophile. And so we have a carbon that is a nucleophile, and then we want to add in a carbon atom that is an electrophile so that they'll react together. And we need a 2 carbon atom chain. So what we really need is 2 carbon atoms with a good leaving group, so something like an alkyl halide. So this could be something like a chlorine or an iodine or a bromine. And then if we have our nucleophilic carbon attack the electrophilic carbon and push off the leaving group, this is where we are forming that new carbon-carbon bond. So these are the 2 carbon atoms we had initially. Here is a new bond, and we've added 2 carbon atoms. So we can explicitly draw them. We could also have drawn that as a skeletal structure. It doesn't matter. So we've got a 4 carbon atom chain. And now to go from this alkyne to the product, we notice that that alkyne is being reduced to an alkane. So we need to do a hydrogenation. And we do not want this hydrogenation, so hydrogenation H2 gas, we do not want this to stop at the alkene stage. So we want to use just a metal catalyst, not the poison metal Lindlar's catalyst, but just something like palladium on carbon. So this is a catalytic hydrogenation. So that's what we call the first step. The second step. The first step, where we are adding an alkyl group to a terminal alkyne, we would say that this is alkylation of a terminal alkyne. So these key terms give you things to search for if you want to look for more information. Okay, so we want to look for these steps put together. So we're looking for a strong base to start with, followed by an alkyl halide, followed by a hydrogenation. So it looks like the option we are looking for is D.